Today's topic in Calculus 2 is going to be sequences using limits, and we are going to go over 3 techniques. One being L'Hopital's rule, where when you have a limit, you take the derivative of the numerator and the denominator. 2 being Squeeze theorem, where let's say you're comparing g of x, f of x, and h of x, mainly g of x and h of x, and if g of x and h of x equal the same exact thing, then your f of x is also going to equal that thing. For example, if your g of x's limit equals L, and your h of x's limit equals L, then your f of x's limit will equal L. And last but not least, absolute value theorem, where if your limit approaching infinity of the absolute value of a of n approaches 0, then the non-absolute value version would also approach 0, which is just your original function. One thing I forgot to cover is factorials. So basically the gist of it is 5 factorial equals 5 times 4 times 3 times 2 times 1, but you don't need to write the times 1. But you could also write it as 5 factorial equaling 5 times 4 factorial. And that's important if you want to cancel out factorials in the numerator and denominator, which I will exemplify for the 4th problem. And also when you have 1 inside the parentheses, just subtract the inside whole number by 1 when you're multiplying it, same as you're multiplying the whole numbers here, and it will look like this. So let's let our first sequence be a of n equals the natural logarithm of n over the square root of n, and let's set n to go to infinity. So again, we're using limits, so let's let our limit go from n to infinity of our natural logarithm of n over the square root of n. Now if you notice, if you plug in your n, this becomes infinity over infinity, which is an indeterminate form, so we can use L'Hopital's rule. So taking the derivative of the top and the bottom, the derivative of L and n becomes 1 over n, and then the derivative of the square root of n becomes 1 over 2 times the square root of n. And rearranged, this is basically the same thing as 1 over n times 2 times the square root of n over 1. So then the limit of n to infinity becomes 2 times the square root of n over n. Now you can look at this square root of n to be the same thing as n to the 1/2. So this is the same thing as 2 times n to the 1/2 over n. So if you brought this n down, you could kind of look at it as 2 over n to the 1 minus 1/2, which is just 2 over the square root of n. And let's make sure to put our limit. And when that n becomes a very huge number, that eventually becomes 0. So this converges. I would now like you to do the second problem on your own. So again, our n is approaching infinity, and we have a cosine of n over n squared plus 1, so let's find that limit. Now when we plug in infinity in our cosine of n, what's interesting is the graph will constantly oscillate, meaning we are always bounded by -1 and 1. And because of this bound, we will use Squeeze theorem. Now the first thing we need to do is to establish our bounds, which is -1 being less than or equal to cosine of n being less than or equal to +1. Now our next step is to then divide all of our parts by n squared plus 1, since our denominator is n squared plus 1. And then our third step is to find the limit of n approaching infinity for the outer bounds, which is the first and the last bound. So let's set our limit as n approaches the infinity of -1 over n squared plus 1, as well as the limit of n approaching infinity of 1 over n squared plus 1. Now, since our denominators on both get so large, they both approach 0. And notice in our little rules over here, if they approach the same thing, L, which in this case is 0, then our cosine of n, which is in the middle, will also approach 0. So our limit as n approaches infinity of our cosine of n over n squared plus 1 approaches 0, which of course converges. So let's let our third problem be a of n equals -1 to the n over the square root of n. And then let's find it as n approaches infinity. So if you notice, plugging in 1, 2, 3, and 4, and then etc. to your n alternates it from -1 plus 1, -1 plus 1, and it just keeps doing that. So what you're going to want to do when you see an alternating sequence like that is to use an absolute value, which is going to be the absolute value theorem. So let's try to set up our limit as n approaches infinity of -1 to the n over square root of n. Now for absolute value theorem, you just take the absolute value of your entire a of n, which you could basically just simplify as taking the absolute value of the numerator over the absolute value of the denominator, which does get rid of the entire hassle of the -1 to the n, making it just +1, and then over the square root of n. Now this makes everything so much more simpler, as this just approaches 0 when you plug in your n, proving that the limit approaching n over infinity of the absolute value of your a of n is 0. Therefore the original limit that was set must also be 0. So your final answer is 0, converges. Now last but not least, let's let a of n equal n factorial over n plus 2 factorial. And of course, let's let n approach infinity. Now what's our goal here? Our goal is to try to simplify these factorials so they can cancel out. So we can mainly tamper with our denominator over here, which n plus 2 factorial just equals n plus 2. And again, remember we're subtracting 1 from the whole number. So it's going to be times n plus 1 and then times n factorial. Now if we just substitute that into our denominator here, our a of n equals n factorial over n plus 2 times n plus 1 times n factorial. Now if you notice, our n's cancel out, so we are just left with a of n equals 1 over n plus 2 times n plus 1. So we could then put that in limit form as n approaches infinity and evaluate since our denominator approaches infinity, and then FOIL our denominator, which gets us n squared plus 3n plus 2, which we can then conclude 1 over infinity, which converges to 0.